So I'm going to start out today by giving a quick overview of my vision of where the future of software engineering and AI engineering is going, which relates to things we talk about in the course, having to do with large language models, ChatGPT, and so on. And the starting point for this was a project I worked on about 3 years ago, began about 3 years ago, which was in conjunction with the Software Engineering Institute at Carnegie Mellon University, the Defense Advanced Research Projects Agency, and the National Science Foundation, where we were trying to think about a roadmap for the future of software engineering. And there's a report that came out here, which you can see, which talks about sort of a research roadmap, a national agenda for this type of topic. And that report was published in November of 2021. What was focused on in that report were 6 major areas, some having to do with how development is going to be done, development of software, of course, as well as how architecture will be done. And it's always hard to know what's going to happen when you start prognosticating about the future. But we were trying to take a 10 to 15-year look ahead. And because of that, we thought we'd be really out there and take some very radical positions about where the world was going to go in that time frame. One of the things we talked about, because we were trying to be long-term thinking, was that the future of software development, which today is very manual, as you all know from the work that you do, is going to be replaced by one where the software pipeline will consist of humans and various AI tools working together as trustworthy collaborators that are going to rapidly evolve systems based on the intent of the programmers and other stakeholders, rather than everything being written in lower-level languages with lower-level tools and processes and methods and so on. So what happened, of course, was that we started off by focusing on these areas, and it turned out that we decided to focus on the AI parts. And what's happened, of course, in the intervening period of time since the study came out is that ChatGPT has emerged and is radically reshaping how people are thinking about things. Originally, we had 2 areas in our study, which came out about a year before ChatGPT did, that talked about so-called AI-augmented software development, which is using AI tools and methods and techniques in the software development lifecycle, and then also engineering of AI-enabled software systems, which are systems where the people are actually using AI for the system's operation. So that's what we started out with. Since that point, we've thought a lot more about this and realized these are not actually 2 distinct topics, but instead they're part of a design space or a space that should be looked at more holistically. And so breaking this down, as we've done in this recent blog posting that we wrote, we realized the dimensions really are degree of augmentation in the software development lifecycle from low to high, and degree of AI augmentation for system operations, low to high. Now, the vast majority of systems that are built today are conventional systems using conventional techniques. They don't use AI in their operations. They don't use AI in the way that the tools and the processes and the methods work. And a classic example of this would be things like avionics mission computing, where you're trying to make sure that the airplane goes on its mission and does the right set of things with whatever it's supposed to carry out. And I did a lot of work on this topic over many, many years to provide support for middleware and real-time quality of service for these types of systems. That's the vast majority of things today are built just like that, especially in mission-critical areas like cyber-physical systems, nuclear power plant control systems, supervisory control and data acquisition systems, commercial avionics, military avionics, and so on and so forth. Where we're headed, and one of the interesting things that we've been doing in this class, for example, is conventional systems built using some AI-augmented software development lifecycle techniques. So, for example, what we've been doing here, where we have our app, the app that you're developing in various ways, different projects, we're starting to use some AI-augmented tools, some code generators. I'm using ways to review, using AI to review the source code that you submit, and so on and so forth. And we're also doing some AI for some of the testing. But the actual applications aren't really using artificial intelligence. Another place here is AI-augmented systems built using conventional software development techniques. So a good example of this would be YouTube, where they have AI-augmented recommendation systems. They have AI-augmented support for trying to figure out what advertisements you might want to watch. and all kinds of other things that they build into the app. But I suspect, at least historically, they've done this mostly with conventional techniques. And of course, the holy grail of where we're headed with all this stuff is AI-augmented systems built using AI-augmented software development techniques. A good example might be a self-driving car that uses machine learning algorithms for its navigation and its decision-making about when to stop, when to go, when to speed up, when to turn, and so on, as well as using AI-driven development and operations tools for making the software, testing the software, deploying the software, and so on and so forth. This is essentially the pinnacle of where we're headed. Now, I have a feeling that we're going to get to that a lot faster for less mission-critical systems than we are for mission-critical systems, because people have to be very careful before they start unleashing automated software that self-learns and self-drives so you can sit there and read a book while you're driving. So let's talk a little bit about AI-augmented software development. So we're going to focus pretty much on this piece down here for right now. So we'll start out with what I like to say is a high percentage prediction, just like a dunk is a high percentage basketball shot, because you're pretty likely to score points if you dunk, especially if you're over 7 feet tall. And the prediction here is that generative AI is having and will continue to have a ridiculously transformational impact on how people are developing software. And this is something that was part of our study, and I think we're looking at this, we're living this revolution right now. So something I believe very firmly, because I'm doing it myself every day, is AI-based tools are increasingly being used to improve the efficiency in which people build software and also the quality of the software and the software engineers by reducing cognitive load. So people don't have to spend as much time wrestling with the nitty-gritty details and can spend more time focusing on things where humans still make a big difference, like architecture, design, requirements, and so on. Certainly for what I do, and I'm sure some of you here as well, are using these various coding assistant tools, AI coding assistant tools like the GNU Copilot or Microsoft Copilot or Amazon Code Whisperer, et cetera, et cetera. And they help quite a bit by making things easier to deal with by offloading some of the work onto automation that is in real time able to help you improve the way you write your code and comment your code. And we're seeing that in a number of different ways. This particular example comes from another course that I teach, which you might want to take in the spring if you like this course, where we're actually developing interesting applications using a whole bunch of AI stuff. And I won't talk about this right now, but we'll talk about this in other contexts if you're interested. I think I mentioned this before. Not everybody is equally excited about how these AI tools are going to help programmers. There's very famous people, my colleagues in the field, like Bertrand Meyer or Peter Denning, who are steadfastly firm in their belief that AI does not help programmers. This is kind of like the famous quotes by, I think it was one of the CEOs of IBM, who said, "The world only has a need for 5 computers." He said this quote like in the 1960s. Or Bill Gates famously saying, "There's no need for, who needs more than 640K of memory?" Right? These are things that are very quickly disproved. So this particular article, which you should read because it's important to know what other people's perspectives are, says that AI is not going to be any help at all. I think people who have that point of view are probably not spending very much time doing programming anymore, and definitely not spending time doing programming with modern tools, where it's incredibly helpful if you spend any time whatsoever using this stuff for real. So what are some of the challenges and opportunities in this space? Well, one of the things that we have to do, and I'll talk about some of the progress we're making, is learn how to train LLMs on better vetted, more robust, and perhaps specialized code bases. Because it's certainly the case that if you give a lot of gobbledygook to an LLM and you give it a bunch of spaghetti code that you might get off the web from Stack Overflow or GitHub or GitLab or whatnot, and you feed it through the process, it's not too surprising you'd end up with output that might not always be as robust and secure as we might want. So what are people doing about this? Well, people are starting to train specialized LLMs in an auto-regressive manner. We'll talk about what that means in a second, based on very large amounts of code. So if you take a look at this article, this is from some researchers working with something called Hugging Face, which is a funny name. using a bunch of different sources, and they're basically training a model that understands how to do code. What does it mean to be autoregressive, you ask? Well, autoregressive simply means that the way that the LLM works is by trying to predict the tokens based on previous tokens. And this is why it takes so long to train models and why it takes so much computational power, because it's very brute force. And essentially, it would try to figure out, based on a bunch of text, what comes after the question mark. So the Trevi fountain is in the center of, and then it builds essentially a model that says, with 96% probability, it's going to be Rome. And believe it or not, this is how they train the models. And it takes a long time, but as we've seen, it works pretty well if you train on useful stuff that actually leads you to meaningful outcome. The strongest language support in CodeGen is for, surprise, surprise, mainstream languages like Python, JavaScript, Go, Ruby. These are the kind of things you're going to find a lot of open source variants that you can train upon. Specialized LLMs are more useful for communities that have very stringent or unconventional quality attributes. So the Department of Defense would be an example. Mission-critical, safety-critical systems like things that run power plants and chemical plants, chemical processing plants, and so on. So in that case, there are often very formalized specifications. This is the one that the Air Force has put forth for designing and evaluating nuclear weapons systems software. It's called the AFMAN for Air Force Manual 91-119 specification. You can actually download it here. It's not classified. And so those are examples of systems with very stringent compliance regimes. And there's also older legacy systems that are developed and sustained using what we would now consider to be non-mainstream programming languages. Things like COBOL, Jovial, Ada, and so on and so forth. So these languages had their time, but very few places teach them anymore. I think I actually learned Ada. That was the second programming language I learned when I went to grad school many, many years ago, like 40 years ago. And it's a cool language, but very few people understand it anymore. However, there's a lot of systems that are built using this software, and there aren't many people who know how it works anymore. So it's one of the things that lends itself nicely to an LLM, because then you can start to replace the lack of humans with automation. Another thing that needs to be done and is being done is to re-envision the software development lifecycle. So there's many different ways to look at the lifecycle. This is not the only way to look at it, but basically you have sort of the planning phase, often called requirements, the analysis phase where you figure out how you're going to go about meeting the requirements through specifying different approaches, the design phase where you figure out the architectural pieces, the implementation phase where you write the code, the testing and integration phase, and then maintenance or sustainment. And this looks like it's sequential in some sense, but it's actually got lots of spirals and iterations all over the place. One of the things that happens in the software development lifecycle is there's an awful lot of data that's generated that is not code. And historically, we've got a pretty good idea, because we're programmers, of how to maintain and sustain code through techniques like Git and so on. But we're not as good about how we capture and leverage the data that's generated throughout the software development lifecycle. There's a nice article here that talks about how to use various machine learning techniques to look at repositories, like GitHub repositories, at the comments and commits that are put in by people when they push their code, to try to get a sense of where the technical debt might occur with the system. So you're trying to give a way for analysts or other stakeholders, quality engineers, to make sense out of where to focus the QA efforts without looking just at the code alone. There's other phases that are important, other documents and other types of information. In fact, there's lots of non-code artifacts that can be analyzed at scale by AI tools, arguably better, faster, cheaper than by humans working alone. And here are some examples of such things. So in the planning phase, you have requirements documents. These would be things that are formally written down. They could also be meeting notes from discussions where people are trying to flesh out what the system ought to be doing. There's all kinds of diagrams. You have UML diagrams of many different flavors. You have mermaid diagrams of many different flavors that try to document the architecture and design. There's test plans. There's test scripts. There's all kinds of things you do for quality assurance, benchmarks. There's things you do for deployment, infrastructure as code with containers and various ways of doing the DevOps processes. And then over time, you also want to be able to continuously evolve and improve the system. And cloud-based approaches make this feasible. For example, people can put new releases of ChatGPT out without you having to install anything new on your computer. And all this stuff is well suited for analysis by something that's automated. If you've ever had to work on a large project with a lot of these documents, you know that people by themselves struggle to deal with this. And therefore, these lifecycle phases, especially the ones where there are not code artifacts involved, are really the sweet spot for generating augmented intelligence, or using generative augmented intelligence, that's people plus AI, because utility, in other words, is it useful, is more important than perfection, often more important than perfection. For the code phases and the testing phases, the gold standard is perfection. If you write code with bugs, it's not particularly useful. If you have test cases that don't cover the tests and the coverage space effectively, it's not very useful. In fact, it's misleading. However, for a lot of these things, you don't need perfection in order to be better than what we have now, which is often not much at all. So for example, one of the things we're doing at the Software Engineering Institute is we're taking documents like the AFMAN that we talked about before, the specification for nuclear weapons safety, and we're analyzing it through LLMs, looking for inconsistencies within the document itself, to see if there's conflicting specifications, conflicting guidance. And we actually have found conflicting guidance in the document. And that's something that people, despite the fact very, very smart people have looked at this document for a very long time, at least 10 years, they still have missed these inconsistencies. Why is that? Because people aren't very good at reading hundreds of pages of text and remembering all the pieces in their head. They're just not good at that, sadly. At least very few people are good at that. I'm not very good at that. So what we need is some way to check things, and LLMs do a good job of that. Some other things that are important is being able to automate different phases of the life cycle beyond just the documentation in order to be able to bring together developers and stakeholders. And there's some interesting ways that people are doing that by using LLMs as an orchestration for a bunch of other tools that they might have in their quiver of QA techniques and assessment techniques. So for example, LangChain provides you a way of being able to use LLMs to bring together a bunch of other more specialized tools that are really custom tailored for the need at hand. So for example, one thing that we're doing, this is also something we're doing with the Software Engineering Institute, is using LLMs plus other analysis tools to check for compliance with the relevant standards and policies in these documents for doing safety, like the AFMAN or other secure coding standards for C++, C, and so on and so forth. And then being able to map the guidance that comes from these requirements documents into analysis of the actual code to see if the code in fact conforms to the rules that are put in the guidance. And this is pretty cool because initially we started out by using static analysis tools, the classic ones you get off the shelf. But now we're moving towards language or LLM-based static analysis tools. We've talked about these in class before, where you can specify what you're doing in natural language or closer to natural language than you would with a traditional tool, which makes it easier for many stakeholders involved in the program to be able to pitch in and help to analyze whether something is going to be compliant or not. Something else that's very near and dear to my heart is formalizing the discipline of prompt engineering. I think this is an exciting area. We're seeing this evolving rapidly as people get more experience using LLMs for real things. What is prompt engineering? There's a couple different ways to look at prompt engineering. One way to look at prompt engineering is learning to program, using that word loosely, with natural language. So rather than having to learn Java or C++ or C# or Python or JavaScript or whatnot, you're problem solving with an LLM using natural language as the vehicle to communicate. The focus here really is on problem solving rather than programming in the traditional sense of using a structured third or fourth generation language. And I think this is very, very, very promising because of something we've talked about before. Most people who are not like us, who are computer scientists, don't want to learn to program. They don't want to have to learn the syntax and semantics of some programming language. They want to be able to apply computation to solve problems in whatever domain they happen to do, be it chemistry or biology or physics or analysis of ancient documents in classical civilization or whatever. And so the LLMs allow you to do this with the proper prompt engineering. One of the other things that we're looking at here is coming up with so-called prompt patterns. Those of you who have taken the 3251 course are probably familiar with patterns, hopefully, at this point. At least some of the basic software patterns, things like the bridge pattern or the observer pattern or the chain of responsibility pattern or the adapter pattern, pick your favorite pattern. And these provide reusable solutions to common problems that occur when we build software. And they provide a template to solve other issues in other contexts through a knowledge transfer mechanism, which is software patterns. Not surprisingly, there are also knowledge transfer mechanisms in the form of prompt patterns for working with large language models. And we have an article here that we published about 6 months ago that's very widely cited that starts to codify and document prompt patterns to make a prompt pattern catalog, like the Gang of Four book did for software patterns, for interacting with large language models. And the cool thing about this is, unlike a lot of the design patterns in the Gang of Four book, by the way, I love the Gang of Four book, but a lot of the patterns are really focused on design for coding, right? So a lot of these things like the bridge pattern, the strategy pattern, these things are very much centric on the coding phase, the design and coding phase, which is fine. But it's harder to apply some of those patterns to upstream activities. One of the things we're doing with LLMs is looking at coming up with prompt pattern catalogs to help automate software engineering tasks further up the life cycle, upstream, as it were, right? Downstream is towards the code and testing. Upstream is towards the planning and analysis and specification phase. And so we're documenting these things, and we've actually got another paper that goes through all this stuff and starts to think through what's going to be required to use LLMs for those phases. Once again, I think that is the sweet spot for LLMs these days, because we're still not quite at the point where all the code that's generated is perfect, all the test cases that are generated are perfect. So people are still a little skeptical. That's why I think some of the people out there like Bertrand Meyer and so on who are like, AI will not help programmers. They're expecting the AI to generate perfect code from high-level vague specifications all the time, which is it's not ready to do that yet. For what we're talking about here, though, it's much, much more useful, especially when humans are in the loop. And then the last piece of the puzzle here, which I think is really the exciting part, and we're going to be doing a lot more work on this over the next year or so, is trying to think through the canonical quality attributes we historically associated with software engineering and then bringing this into the world of prompt engineering. What the heck does that mean? Well, if you think about the way people historically have built systems for software, there's the design and coding part, which is what we do in this class, which is fun. But there's also these other things you got to deal with. You got to figure out how you're going to do requirement specification, how you're going to do things like configuration management, how you're going to do testing and maintenance and release-to-release compatibility. These are the kind of things that people who build large systems, especially mission-critical systems, really struggle with, because if they screw it up, then the system doesn't work, and you spend billions of dollars and you end up with something that isn't effective, like the Affordable Care Act software for many years. It didn't work very well until they finally got their act together. Same thing is going to be true and is going to be more true in the future for prompt engineering and using LLMs. Right now, most of us, when we use LLMs, use them in very localized, sort of tactical ways. We're not trying to build a system that's going to last 70 years using today's LLMs. But people are going to be doing that because people are going to be relying more and more on these things. The problem is, with every new release of the LLM, it's possible that something that used to give you sensible results doesn't work anymore. So release-to-release configuration management, testing, quality assurance, all the same things we think about when we try to engineer large-scale software programs that need to work, mission-critical, safety-critical, life-critical, are going to have to be thought through for prompt engineering and use of LLMs. And people are only beginning to scratch the surface of this. And what I think is so funny is a lot of people have taken a very narrow view of prompt engineering to think, oh, that's just the way we have little parlor tricks to get the LLM to do our bidding. And very soon, the LLMs are going to be so smart, we don't have to do these parlor tricks anymore. Wrong. If you spend any time with LLMs, you know that English and whatever language you use to communicate with them is inherently imprecise. So you're going to have to learn to be precise because it's not like C++ or Java or Python where there's more specific semantics associated with the different statements you can do. Number one, so we're always going to have to figure out ways to express ourselves clearly. But number two, prompt engineering, if you look at engineering of the prompt engineering, isn't just about how you express stuff to the LLM. It's how you manage the LLM's interaction with you over time through these other phases of the life cycle. So that's basically the end of that discussion. You've seen this other stuff before. We've talked about that. But I wanted to make sure that I had a chance to kind of give you the big picture view of one piece of how I see the future of software engineering changing with the introduction of LLMs. And once again, you guys are at the forefront of all this stuff because this is really the first semester where we've actually taken it seriously at Vanderbilt and focused on how to start teaching these things systematically. I suspect it's going to take a number of years before people figure out what we really need to be teaching in this space, which is tricky because it keeps changing very fast. And so it's kind of like the early days of programming where people didn't quite know what the right languages were, they didn't know what the right platforms were, they didn't know the right methods. We went through a lot of sort of false starts, starting with smaller scale approaches. If you go back in the history of computing and you look at software design in like the 60s and 70s, a lot of it was based on so-called stepwise refinement and top-down design, where you'd start out with a specification of something and you'd refine it based on its functions. And then around the 1980s, mid-70s to 1980s to the 90s, people realized that really wasn't the way to do things. Better way to do things was to break up your system in terms of modular components, classes, objects, packages, and so on, and try to rethink in terms of these more stable properties. And then people began to learn in the 2000s and beyond that, gosh, there was actually some benefit to thinking about things functionally. So now you see the resurgence of functional programming. But in my mind, at least, those types of things are best understood when you wrap them in the overall structure of some kind of object-oriented decomposition. So you have the structural parts based on classes and objects, and then you have the behaviors and the computations done functionally. And those are nice combinations. And that's, of course, what modern languages do. Python, Java, C#, I guess arguably JavaScript, although I think that's an abomination. Maybe TypeScript, we'll say something nice about that. That's at least somewhat structured. But the point is that these things are evolving, and it's going to take a while before people really understand how to use the LLMs most effectively in our processes for software development.